Alrighty. Oops, I guess I should clear that off there. He, he. All right. All right, so last time in class we learned about the product rule and quotient rule. Those were not necessary on your most recent quiz, right? You did not have to use them. But just to refresh your memory a little bit about that product rule, right? Whenever we have the derivative of a product of two things. By the way, the product rule, you could even apply it if you wanted to for situations where you have like, y equals 5x. You could treat that like a product and take the derivative of this thing as if it were a product. You would still get, when you do that, you would still end up simplifying down to just 5 if you do the derivative of something like it's a product. Because it is a product, technically, right? But we can also just use that power rule and the coefficient rule, I think is what we call it. Right? So anyway. So the derivative of a product here is down here, right? It's the second times the derivative of the first plus the first times the derivative of the second function there, okay? When you break it up into two pieces. All right, we did some problems with that. And then we also looked at the quotient rule, okay, which is when you have a quotient. Again, that was like, well, again, you could have used it on the quiz if you wanted to. You didn't need to, okay? But the derivative of a quotient is not simply the derivative of the top over the derivative of the bottom. It is not that, right? It is this complicated kind of, expression here. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Similar to your product rule, but not the same, right? There's some similarities there. And of course, then I gave you this little memorization tool to help you. Mr. Goff calls it the yodel, I think, or something like that, the calculus yodel, but low d high minus high d low over the square of what's below. Okay? I thought it sounded more like something like a leprechaun would say, but, to each his own. Okay? And then we did some problems with that too. All right, moving on. Now, we're going to apply this quotient rule to figure out the derivatives of some of our other trigonometric functions that we have not, talked about, right? So we did sine and cosine. We know their derivatives. But what about tangent, cotangent, secant, and cosecant? Of course, we can't leave those guys out. So let's kind of discuss here how we can use the quotient rule for this. All right. How can we rewrite tangent, for example, as a quotient? The tangent is quotient of what? Sine over cosine, right? So taking the derivative of tangent with respect to x is the same thing as taking the derivative of sine of x over the cosine of x with respect to x. Now this is helpful for us because while we do not know the derivative of tangent, we know the derivative of sine, we know the derivative of cosine, and we know the quotient rule. So we can take the derivative of this thing that's equivalent to tangent using that quotient rule. Okay? So the derivative of this will be the bottom, right? Cosine x low times the derivative of the top. The derivative of sine is cosine minus the top, or high, times the derivative of the bottom, or d low. So the derivative of cosine is negative sine all over the bottom squared. Okay, all over the bottom squared there. All right, so we can simplify the sum, right? Cosine times cosine, cosine squared. Minus cosine times a negative, minus cosine. Minus sine times a negative sine becomes what? Plus sine squared x over, and then I'll go ahead and just square the cosine there and call that cosine squared x. Okay. Now, we end up with this, but what is the cosine squared of x plus the sine squared of x equal to? 1. That's one of our Pythagorean identities that we wanted to recall. Remember something we saw back in our summer review packet. So we get 1 over the cosine squared of x, which we also could rewrite as what? Secant squared of x. So the derivative of tangent is secant squared of x. Okay. Derivative of tangent, secant squared x. So now we have a new thing. Yes, Sean.
Can we, so if we,
Never mind. Okay. You got it. All right. By similar argument, we can do the same thing for cotangent then. By similar argument, we can do the same thing for cotangent. So cotangent is a quotient of what two trig functions? Cosine over sine. Okay, cosine over sine. And again, I remember that tangent is sine over cosine. Cotangent is cosine over sine. That's how I would remember. Then the cotangent, cosine over sine. If you need help remembering that, then there's something for you. Again, quotient rule here. Bottom or low sine of x times the derivative of the top. Derivative of cosine is negative sine. Minus the top cosine of x times the derivative of the bottom, another cosine x, all over the bottom squared sine of x, that quantity squared. Okay? And so then we multiply. We have a negative sine squared of x that we're going to arrive at there, minus cosine squared of x, all over sine squared of x. Does negative sine squared minus cosine squared equal 1? No. But since they're both negative, we can factor a negative 1 out and make it sine squared x plus cosine squared x all over sine squared. I'm running out of space here. Okay, so again, from that numerator, right, since they're both negative, we'll factor a negative 1 out, making them now both positive. And of course, what is sine squared of x plus cosine squared of x equal to? 1. And so we end up with negative 1 over the sine squared of x, negative cosecant squared. Sorry, I'm like blocking with my hand there. Okay, so the derivative of cotangent is negative cosecant squared. Okay, now, I feel like I can remember back when I was in calculus, like you guys are right now, in my high school class, all right? And I hated memorizing things. And so in a situation like this, you absolutely could, memorize this derivative of tangent is secant squared of x, right? I preferred to just remember how you would derive that, right? So in other words, I would remember, oh, tangent of x, that's sine over cosine, and then I would just take the derivative if I needed to end up to that, if I forgot it, okay? So in other words, I would still suggest memorizing this, but if nothing else, remember how we did these derivatives, okay, and then use those methods to just, rederive whatever, the derivatives are there, okay? So you can remember this too, right? You can memorize it, but you can also then, just redo it if you need to in a test or quiz situation. Of course, that's going to eat up time, but, that's, at least that's an option for you, a strategy you can use. All right, so tangent was sine over cosine, cotangent cosine over sine. How are we going to rewrite secant then so we can take its derivative? 1 over cosine, right? Put it in terms of something whose derivative we know. So yes, it's 1 over cosine. Okay? And again, we'll take the derivative using a quotient rule here. Must use the quotient rule. We have a quotient, must use the quotient rule. So the bottom, cosine x times the derivative of the top. What's the derivative of 1? 0 minus the top. 1 times the derivative of the bottom. What's the derivative of cosine? Negative sine all over the bottom squared. Okay, we simplify here. 0 times cosine, 0, right? Negative sine times a negative 1, positive sine of x, all over cosine squared of x. Okay, and while this is so, typically, anytime you look up, if you were to look up the derivative of secant of x, this is not where we leave things. Typically what we do is we rewrite this as 1 over cosine x times sine x over cosine x. Okay. Do you believe that is equivalent there? Yeah.
How did you get rid of the negative 1 again?
Right here. So it was cosine x times 0. So that left that whole quantity there was 0. And then it was a minus 1 times negative sine of x. So negative 1 times negative sine positive sine. Okay, and thank you for asking. Okay, that's another thing, folks. Please feel free. Right? I don't know if you just don't want to be the only person asking questions in class. Please ask questions. Okay, please throw your hand in the air or just shout it out if you really need to, whatever. But please feel free to ask questions. All right, don't just let these things go by you. Okay, and just be like, that didn't make sense, but no one else is going to ask this question. I'm going to feel dumb. So please ask a question. Anyway, we break up our denominator, right? And we're all okay with how I did that there? These would be equivalent, right? So what is 1 over cosine? Secant. What's sine over cosine? Tangent. Okay, so the derivative of secant x is secant x times tangent x. How interesting. Okay, it shows up in its own derivative with more stuff. Okay, and then cosecant's derivative is done by a similar fashion there. Okay, actually I think I'm just going to skip through that and just give you the answer. So cosecant's, by similar kind of setup to what we did here, it's going to end up being equal to negative cosecant x cotangent x. Okay, I'm not going to spend the time going through all of that. All right, now, these wouldn't be too bad, right? You do need to memorize these, but these wouldn't be too bad if we didn't have to worry about these tricky little negatives and like when they show up. All right? Well, let me kind of help you at least realize when you're going to have to deal with the negatives with the trig stuff. The derivative of cosine is what? Negative sine. The derivative of cotangent, negative cosecant squared. The derivative of cosecant, negative cosecant cotangent. Okay? So anytime you take the derivative of a co-function, cosine, cotangent, cosecant, anytime you take the derivative of those functions, you'll have a negative derivative as your answer. As opposed to sine, tangent, and secant, all those are positive. Okay? And they're, closely related. Tangent's derivative is secant squared, so it makes sense then, cotangent will be negative cosecant squared, right? Secant is secant tangent. Cosecant is negative cosecant cotangent, okay? So they're related there. There's ways to memorize them, and you do need to memorize them, all right? So, number 4. Actually, any questions before we move on there? All right, moving on. Number 4, we're going to find the instantaneous rate of change of y equals cotangent x over 6x squared, which means we need to take the derivative. So you guys, go ahead, do that, okay? Number 4, take the derivative. Yeah, you don't have to simplify it if you don't want to. Yeah, that's fine. All right, so here, hopefully, is what you got. Okay, 6x squared times negative cosecant squared minus cotangent x times 12x all over 6x squared quantity squared. That is a quotient rule, okay? Again, we cannot take the derivative of that original function, the cotangent x over 6x squared by just taking the derivative of the top and putting it over the derivative of the bottom. That's not how the derivative works. If it's a sum, then absolutely take the derivative of the individual pieces, add them together. If it's a difference, take the derivative of the individual pieces. A quotient or a product, we have to use those rules. That's why we have them in the first place. Okay. So, why?
Why is it local linear?
Why is it that?
Why?
So, because, let's think about this, all right? If you take a look at a function, so let me just, I'm not going to graph that. That's just kind of crazy to look at, but let me just graph like a nice quadratic there, right? All right, and let's just pick a point along here. Okay, and again, if you'll permit me, I'll just go ahead and just like graph a tangent line. I'll eyeball it, kind of thing. I'm not going to actually calculate. But it's going to look something like that, right? Where it's going to intersect with that single point and give you the slope of the function at the particular point. So local, that means nearby, linear, so we're using a line to approximate the original function. So you can see that in this little neighborhood around that point of tangency, the equation of the tangent line is a pretty good approximation of the original function. The reason why this is useful is because sometimes we're able to come up with the equation of the tangent line without using the actual function or having like an idea of without having an idea of the entire function kind of thing. So it can be helpful, or especially for calculations and stuff like that. Okay, so that's an excellent question, right? So when we talk about a local linear approximation, that's really using the equation of the tangent line to approximate our function here. Okay, so in other words, we need to come up with the equation of the tangent line. Okay, so what do we need to write the equation of a tangent line? Slope and a point. Okay, how do you find the slope of your tangent line? Take the derivative of that original function. Okay, so let's do that. Y prime equals, what are we going to do here? What do we need to use to take the derivative of this? It's a product. There's your F, there's your G. Okay, if you need to, underline the two pieces to help you organize things. So it's the second times the derivative of the first. What's the derivative of x? 1. Plus the first, x, times the derivative of the second. What's the derivative of secant? Secant x. Tangent x, that's right. Do not forget the x's, all right? That's important here, all right? All right, we've taken the derivative, so this is my slope? No, now what do I need to do? Because we want to find the slope at a particular point. This derivative describes all of the slopes of this function at any particular x value, but we want the specific slope at pi. So we're going to take y prime and evaluate it when x is pi, and so it'll be secant of pi times 1 plus pi times secant pi tangent pi. I don't know why I put a parenthesis there. So I should put it there. Okay. All right. So secant is 1 over cosine. Cosine of pi is negative 1. 1 over negative 1 will still be negative 1 times 1. Plus pi times, secant of pi we just said was negative 1. Tangent of pi is going to be, 0. Okay, so this product right here is all 0, and then this slope is going to be equal to negative 1. Okay, so we got the slope, so that's our answer. And then we're supposed to write the equation of the tangent line, so we need to come up with our equation. So, okay, y minus, equals negative 1, our slope, times x minus, what's our point here, Gabe? Oh, you have a question? Sorry.
Yeah. So you use the product rule, right?
Yes. The derivative. So there's g of x. There's f of x.
It would be pi, right?
Say again?
It would be x minus pi.
Oh, sorry. To answer my question now, yes. Our x coordinate's pi. What's the y coordinate here for our point slope form? Where'd that come from? You got to plug it back into the original function. Yes. This point, the point is not only a point on our tangent line, but it's also a point on the function, right? It's where the tangent line intersects the function. It is this point right here. Okay, well, not on this particular function. But you get the idea. It's that point. The point of tangency is shared by the function and the tangent line. So we can use the function, plug pi in. Secant of pi was -1 times x, which is pi, so it'll be negative pi. There's the equation of your tangent line. Okay. So the slope goes there, and then, y evaluated at x equals pi is that negative pi. Okay, right there. Questions on any of that? Tangent line. Okay, tangent line. Local linear approximation. You know what? I'm going to go to my calculator just to show you here. Okay, just to show you this. X times 1 over cosine x. Oops, nope, I also want a graph. And then -1 times x minus pi minus pi. Right, plus pi minus pi. Yep, okay. So here I'm going to, and you don't need to do this if you don't want to, but I'm going to. Okay? I'm going to graph our function, x times the secant of x. I'm also going to graph our tangent line, okay, slope of -1, x minus pi, and then it was going to be y plus pi, and so I subtracted pi over. So if I graph this, okay, there's my tangent line. I'm graphing that first. Okay, let's see here, x secant x at x equals pi. Okay, make sure I'm in the right mode here. Ah, that's the problem. I was in degrees because I was checking people's work with the degree mode there. Okay, and so there's our tangent line right there. Mr. Witt is going through the other part of the function, I know. But at pi, if I go to value here, at pi, you'll see pi. Question? Oh, okay, thank you. Okay, so you can see here in this little area at pi, there's that nice tangent line. If I do the zoom here, I'll do zoom box. Okay, if we zoom in on this, right? There's that x secant x. There's our tangent line. And so you can see that as we get closer to that tangent point, the local linear approximation, our tangent line, is going to be a pretty good approximation for the value of the function, right? Especially around that point of tangency. Let's see if I do intersect. Hopefully it will work. Yeah. So there we can see at that point of tangency, the closer you get, the better approximation that line is to that function. Okay? So that's why we call it that. All right, questions on any of that? Okay, moving on. The next idea here that we want to incorporate too is the idea of a higher order derivative. All right, so higher order just means that we can take derivatives of derivatives. All right, so the second derivative, for example, is the derivative of the first derivative, right? When you take a derivative, you end up with a function, which you can also take the derivative of that, and then keep on going, so on and so forth. So we denote that as f prime prime. Okay, you could also see it written this way, the derivative of f prime with respect to x. And then in that dy dx format, here's how that kind of ends up. D squared y over dx squared. That also means the second derivative. So this, and this all refer to the derivative of the first derivative, or in other words, the second derivative. And of course, the third derivative will be the similar kind of situation, f prime 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 of x, or the derivative of f prime 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 x with respect to x, or the second derivative of f prime, right? So the third derivative is really the second derivative of f prime, so on and so forth. And then if you really wanted to, you could also say d cubed x over dy, dy cubed. D cubed y over dx cubed, okay? All of these mean the third derivative, and so on and so forth, right? So on and so forth, okay? So for example 6 here, I'd like you guys, well, let's go ahead and find these derivatives here. So f prime of x, let's find that first derivative, okay? So what would the derivative of f of x be here? The first derivative be 4x to the third minus 9x squared plus 2. That's it. Good. Okay, stop. Right? Derivative of negative 17 is 0. You can put a plus 0 if you really wanted to, but no point. There's the first derivative. All right, let's do the second derivative. F prime prime. Okay. 12x squared minus 18x. That's it. Derivative of 2 is 0. Okay. F prime prime prime. Derivative of 12x squared. 24x minus 18. Okay. F prime 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 prime. 24. Okay, and then the eighth derivative, f prime 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 prime. Just kidding, we're not going to do that. Parentheses 8. Parentheses 8, okay? Once you get to a certain point, it's too many primes. And so you just put parentheses around the number of the derivative. Exactly, yeah. Just fill your pages up with those primes, okay? And so what would the eighth derivative be? 0. Okay, what would the 100th derivative be? 0, right? So your polynomials, they kind of keep reducing in power until eventually they end up at 0, okay? These nice polynomials and stuff like that. Okay, some other things that you'll notice, trig functions can be cyclical. So for example, the derivative of sine, okay, you could take the derivative of that, so I'll just do it here, why not? So, if we have sine, for example, derivative of sine of x is what? Cosine x. Okay, the second derivative then, what's the derivative of cosine? Negative sine of x. Okay. This third derivative here, what's the derivative of negative sine? Negative cosine. And then the derivative of 1, 2, 3, 4 there, the derivative of negative cosine, back to sine. And then this pattern repeats. Okay, so we go there. And so that's where you can sometimes get some fun questions like, what's the 99th derivative of sine of x? And you can be like, all right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or you could also, use your 99 and then divide by 4 and get the remainder and then use that to help you figure it out too. Or you can just do it 99 times. So Mario is a fan of the brute force method there. So there you go. And that's a thing that you can do. All right. So yeah, exactly. All right. Moving on here. For this next one, you definitely want your calculator. Oh, sorry, Cindy.
What does the second derivative mean? Why is it important for the priority?
We will see a application of it, the second derivative at least, in just a few moments. So hold that thought. I'm glad you asked. You can think of it right now, Simeon, and for everybody. Okay, you can think of the second derivative, right? So let's think about this. The first derivative. What do we use that? What do we call that? Slope of our original function, the instantaneous rate of change of our original function, the tangent slope to our original function. So the second derivative would be all of those things to the first derivative. The second derivative is the instantaneous rate of change of the first derivative. The second derivative is the slope of the first derivative at any particular point. So that's, in basic sense, but then we'll see application 2 in just a little bit. Okay? And some of you physics folks already have an idea about what I'm talking about. But anyway. Real-world application. So prior to calculus, people could only measure rates as average rates of change. For example, if you drove 60 miles in 1 hour, then you know that you traveled an average of 60 miles per hour, but you didn't necessarily drive 60 miles per hour the entire time at a constant rate, right? And most likely you didn't. So cruise control, true. But even cruise control, if you go up or down a hill, you'll see your speedometer, do change a little bit. If you're on a flat surface, probably, though, it would be about exactly 60. Anyway. That, however, does not tell you how fast you traveled at any moment. So introducing calculus, we can now determine the instantaneous rate of change, right? We knew this already. So for example, you can now determine how fast you traveled at any moment along the hour-long trip. Okay, so let's take a look at example 7 here. We're talking about the height of a tree in feet is modeled by this function. Okay, and so you'll see here we got some stuff going on in there whose derivative we can't take, where t is in years. Okay. First thing we're asked to do is find the average growth rate. Okay. When we see that word average, it's a slope, but it's not the slope of the tangent line. It's the slope of the what? The secant. How do you find the slope of a secant line? We're going to be using y2 minus y1 over x2 minus x1. The good old slope formula from Algebra 1. Okay. If we're trying to find the average growth rate from years 1 to 4, those numbers are, what are we going to consider those to be? From 1 to 4. Are those y values, x values? those are our x values. I guess really in this case they're t values, right? But so yeah, so our slope formula is going to be, I'll do 4 minus 1 in the denominator for our t values there, okay? Okay, and then what about the y values? How do we figure out those? Plug them into the function. So this is, in this case, it's really h of 4 minus h of 1, which is going to be, and then that's why we have our calculator, okay? Make sure your calculator is set to radians, please, because we are dealing with cosine here. Put my light back on. All right, so let's see. So, by the way, for those of you that aren't so familiar with your calculator, let me show you a little trick here, right? I know that I'm going to be plugging in 2 different numbers into my function. So one way you can kind of make that a little bit easier for yourself is to use the store command. So if you press the number 4 and the store button is right above your on button there. Okay, you get this little arrow, and I'll put it in for x. Okay, so 4 store x. So now anytime I use x on my home screen, it's a 4. So now when I go to type this in, I can just do 0.55 x squared minus 3 to the 2 minus x times cosine x. Right? Makes it a little bit nicer than having to type in the 4. Maybe. I don't know if it's that big of a deal for you, but there it is. You can hit enter, and there's our answer. 8.873, we'll say. Minus, and then h of 1. Now here's the magic, right? So I can now do, once I've got that answer, I can now do 1, store it in for x. Okay, store 1 in for x, hit enter. And now I can go back up to the thing that I had typed. It'll copy it back down there, and now it's going to evaluate it at 1. So I get negative 1.071, we'll say. And that's all over 3. Okay. So there it is. And of course, then I'll finish this off. 8.873 minus negative 1.071 all over 3. And so there's our answer. 3.315, we'll say. Well, good question.
It was in the ground.
Yes.
The roots were
There you go. There you go. See? There you go. Exactly. The tree was still working its way up there. But truly, you're right. In this situation, this doesn't make sense for the context, I guess. But that's the idea, yes. Okay. Yeah. No. It's a good question, though. All right. Anyway, moving on. So there's the average rate of change. Now, you'll notice we want to find the growth rate then at t equals 3. So that's at an instant, right? So we have the average growth rate right here. We also want to find the growth rate at an instant. How do we find the growth rate at an instant, at a single point? What do we use? The instantaneous rate of change. It's the derivative, right? If this is describing the height, so if h of t means the height at time t, then h prime of t is equal to the rate of change of the height at time t. Okay? If h of t is the height at time t, h prime of t is the instantaneous really rate of change of the height at time t. Okay. So go ahead and take the derivative of that. Trick question, we can't. Okay? We don't know how to do that yet. Eventually we'll actually know how to do that one, I think. Yep. But we can't. So we're going to use our calculators. How do we use our calculators to take the derivative? You have a couple options. You have math 8. Okay, well, you can do math 8, or you can also do second trace and do it in your calculate menu too in your y equals. Okay, so let me show you 2 ways. You can do it whichever way you want. Option 1, type your function whose derivative you want to find into your y equals. So 0.55 x to the 2 minus 3 to the 2 minus x cosine x. Okay. So that I typed it into my y equals, That graph is very interesting. Okay, not too shabby there. All right, so there's my graph. I want to find the growth rate at t equals 3. I'm going to find the slope of this thing at 3. So if you do it the graphing way, you'll press second trace, and you'll scroll down here to number 6, dy dx, the derivative, right? Question?
How do you clear the store that you did?
You clear the store. You really don't ever. You're actually your graph always, or your calculator always keeps some value in for x. It won't affect your graphs. It only affects stuff on the home screen. So anytime you use x on the home screen, it'll be that value. Anytime you use something like graphs, it's just the variable x. That's it.
Store it as X.
Maybe. Infinite loop. All right, so anyway, we hit dy dx. Nothing happens because it's waiting for us to give it the value at which we want to find the derivative. So we're going to type in 6. So we'll see at x equals 6 there. We hit enter. Was it 6? No, it was 3, Mr. Wid. Because 6 was the number that we used for dy dx. 3 is where we want to find the derivative. And so there's our derivative value. dy dx, see, it labels it out there for you, 2.985. I'll round that too. H prime of 3 equals 2.985. Okay? So that's one way to do the derivative. Okay? This is good. Now, when we want to evaluate the derivative of a function and we have our calculators available to us, we can simply get the calculator to give us the value of the derivative. What can't our calculators do? Our calculators cannot do the derivative for us, right? So if I ask you to just find the derivative of this function, your calculator won't do that, or at least not these, and no one's got a TI-89. Okay, the TI-89s will actually like do a symbolic derivative, like we'll actually do the derivative of this and give you like the function. But none of you have that calculator. And yes, it is legal on the AP test. So why doesn't everyone use that? Well, because there's more to the AP test than just taking the derivative of something. That's like step 1, and then step 2, 3, 4 is like actually like analyzing your answer and stuff like that. Anyway, option 2 for how you find the derivative of this thing. You can go to the question. Okay, I'll come take a look at that in a second here. Make sure your plots are off. If you go to your y equals and make sure your plots are all off too. Sorry, math button, arrow to you said it was num, right? And then 8. Not for me though. Oh, math 8. Sorry, thank you. You can see it says n deriv. Okay, that's numeric derivative. Or in other words, it'll help you find the value of the derivative, but not actually take the derivative. If you have a nice calculator like mine, when I hit enter. Oh, it's beautiful. Look at that. Okay, so I have to tell it I'm differentiating with respect to x. I'm going to tell it the function. Okay. So 0.55 x squared, put the function in. And then at the very end, you'll see evaluate it. There's our vertical bar there. At x equals, for us, it was 3. And I get the same answer, 2.985, 2.985. Yes, if you have the uglier version.
Thank you.
Sorry, shots not trying to be fired there, but just, I don't know how to describe it other than that. All right, that's what it would look like. That's how you want to type it in. N deriv the function with respect to x, so comma x, comma 3 where you're evaluating. So function, comma, with respect to x, comma, the value which you're trying to evaluate the derivative, 3. Okay? Just like that, you hit enter, you get the same answer. Okay? And this might be helpful, right? So again, the command would be n deriv, parenthesis, function, comma, x, comma, value. Or okay. So that's your command you're going to use if you don't have the nice pretty type on your calculator like I do, and some of you all do. Okay. We're not done yet, because at the very end we must give units. Okay, and that's going to be true in general. So one additional step we need to be comfortable with when we're in a context is giving correct units. Okay. For our original function, what would values of h, what would we say for values of h there? H is in what units? feet. It says right here, right? Height of the tree is in feet. In this case, sometimes it's meters, sometimes meters, but in this case, feet. Feet. Okay? What would then h prime, the rate of change of the height, what would its units be? If feet is the original units of the height, what would the rate of change of the height be called? Feet per unit of time. In this case, it's t is in years. So yes, it's feet per year. And here as well, for the average rate of change, that would still be labeled as feet per year. Okay, you may use abbreviations for your units. Feet per year. Okay. Think about it like a slope, right? Okay, I mean, think about your average rate of change here. We subtracted heights on top. We divided by time and years on the bottom. So it's feet on top per divided by year. Feet per year, right? Here for the rate as well. Feet per year. Okay? All right, let's take a look at number 8 here. You guys read through that and pick what you think is the correct answer. This is multiple choice, and this is taken from an AP test. Okay, so read through that, and using what we know about the derivative, units, and how we apply that stuff, see if you can come up with whether it's A, B, C, or D here. Only one answer is correct. Remember, you're trying to interpret the meaning of C prime. C prime of 500 equals 80. So what does it mean? What do you think? What does it mean? If nothing else, see if you can eliminate some answers you're pretty sure are not right, right? At least you can try and do that. Try and eliminate answers that you're pretty sure are not right. If you're not sure.
I'm gonna come out and see you guys wrong.
Question. Oh, right. You didn't get it fixed. Did it work?
No. I usually
Did that work?
Am I being the stairs? I'm sure I'm saying. Wait.
So X there, you can try to punch in there, and evaluate it. It will X will show. Second trace, calculate 90 by the X and type in value 6. Or sorry, 3. It's 3. Okay, real quick here. Before I give the answer, before I reveal what the answer is, and I walked around and some of you had it, some of you didn't. Okay, that's okay. Let's talk about what this function is. So we have the cost in dollars to shred the confidential documents of a company is modeled by C. So C is a cost, okay? And C is a differentiable function of the weight. So it's a function of the weight. So it's cost of the weight. So the weight is our independent variable here. The cost is the dependent variable. The cost depends on the weight of documents, okay? And so then when we take the derivative here, okay, if the cost is related to the weight, right? So then when we take the derivative of cost, now we're talking about the rate of change of the cost, right, with respect to the weight. And so what would the answer be here? I just confused a bunch of people because people had the right answer. So it's D. It is D. Okay? It is D. The cost to shred documents is increasing at a rate of $80 per pound. We throw in the increasing. Why do we throw in the increasing here? Well, because it's a positive E. That's equal to there, positive E. So yeah.
So if it was just C of W instead of C prime of W, A would be right?
Say it one more time, sorry?
So since A is the cost to shred 500 pounds,
That would be C of 500 equals 80. Right, yes, exactly right. So A is saying C of 500 equals 80. But we're asked what's C prime. There's a little prime there, right? So it's not letter A. The average cost to shred documents is $80 or $500 per pound. Again, average, if it's C prime, we're talking about instantaneous, not average. And then, sorry. Oh, it's frozen, sorry. Thank you. And then, Clayton, question?
So is it kind of like saying at the point 500, the slope is 80?
The rate of change of the cost is $80 per pound.
Right.
Yes. So you know, at 500, you're increasing your amount of money you're going to be spending by $8 per pound of, you know, waste documents. Okay. Questions on that one? Important application there. Okay, so it is letter D. The cost to shred documents is increasing at a rate of $8 per pound when the weight of the documents is 500 pounds. Okay. Moving on here. All right. We're going to look at some particle motion stuff. Oof. All right, we'll see how we do here. All right, so here is what Simeon was wondering about. Okay, in discussing motion, there are three closely related concepts, so another application of the derivative here that we're going to see, another context, and this is a context that is like a pretty big one, right? Like we're not going to do like repeated problems dealing with heights of trees. We're not going to do repeated problems dealing with like, you know, costs of weights of documents and shredding and stuff like that. We will be doing repeated problems here with particle motion because there's so many applications of, so many different ways you can apply the calculus here. Okay, so the three big concepts we're going to talk about are position of a particle, velocity of a particle, and acceleration of a particle. Okay, the position of a particle will typically be described as x of t or sometimes s of t. So obviously t meaning that the particle's position is dependent on time. Okay, so x of t or s of t. The velocity, of course, v of t will be the typical name for velocity. And acceleration, of course, we normally expect it'll be a of t there for acceleration. So those are kind of the typical ways that we will name things. But of course, this is calculus, right? So how are these things related? Well, the velocity is the derivative, or the rate of change, instantaneous rate of change of the position. Okay, your velocity is instantaneous rate of change of the position. Acceleration, well, that's the derivative of the velocity. It's the rate of change of the velocity, right? If you accelerate, that means your velocity is increasing. If you decelerate, that means your velocity is decreasing, right? You're changing the rate of change. It's the rate of change of the velocity. And since a of t is the first derivative of velocity, and since the velocity is the first derivative of the position, what can we say is also, how can we also relate the acceleration to the position here? How does the acceleration relate to the position?
Second derivative.
Second derivative, x prime prime or s prime prime, yes. Okay, so acceleration is also the second derivative of the position. Okay, now we got all these blanks to fill in here because there's that with that kind of relationship, we have all these kind of like ideas that can come in, all kinds of contexts that we can think about. Okay, so if x of t represents the position of a particle along the x-axis, so again, along the x-axis, this is crucial. Okay, along the x-axis. Sometimes it'll be along the y-axis, and so we'll have some subtle changes here to this. But if we're assuming along the x-axis at any time t, then this means initially, if you see the word initially, that means when what is equal to 0? The t in this case, right? T is our time. So when time equals 0. At the origin means x of t or s of t equals 0. It's position, right? Again, if we're talking about the function describing the position of the particle, then if the particle is at the origin, that means its position is 0. Its x of t or s of t is 0. Okay? At rest means which one of these is equal to 0? Velocity, right? If you're not in motion, then your velocity is 0. Not necessarily. You could think about, for example, a ball thrown up into the air, right? A ball thrown up into the air will decelerate, eventually have a velocity of 0, but then immediately start going right back down. So at an instant, you could have a velocity of 0, but then, yeah, the acceleration would still, like gravity is still affecting the ball even when its velocity is 0. So good question, though. All right, if the velocity of the particle is positive, then the particle is moving to the right, right? If we're moving along the x-axis, we're talking about a positive velocity, then it's moving to the right. Likewise, then, if the velocity of the particle is negative, then we'll say the particle is moving to the left. Okay? And of course, correspond those things to the axis that your particle is moving along. So for example, if our particle is instead moving along the y-axis, a positive velocity would indicate the particle is moving up, and a negative velocity would indicate the particle is moving down, right? So just keep in mind about your, what you're moving along and stuff like that. To find the average velocity, so keyword average, over a time interval, divide the change in blank by the change in time. Divide, not the velocity actually, divide the position. And this is where students sometimes have some trouble, okay? When we talk about using the slope formula, right? We use the slope formula when we're trying to find an average something, right? When we're using the slope formula to find the average, that slope formula is for an average rate of change. Is this thing instructing us how to find the average rate of change of the velocity? It's just saying to find the average velocity. The velocity is the rate of change of what? Position. So when we say average velocity, we could equivalently say rate of change of position. Right? Anytime you see the word velocity, you can substitute that for rate of change of position. Why is this significant? Because now we can maybe have a better idea about why we're dividing the position by the change in time. When we're asked for the average velocity, that's really asking for the average rate of change of position. That's a slope with position subtracted on top and time subtracted on the bottom. Okay, and so this is what's said right here. This is the average rate of change of the position function. Okay. So anytime you see the words rate of change of position, you can exchange that for the word velocity. So average rate of change of position is average velocity, and vice versa. Okay. Instantaneous velocity is the velocity at a single moment, instant in time. This is the instantaneous rate of change, aka the so first of all, what besides instantaneous rate of change, we know that as the derivative or the slope. You can think of it that way, but I think the derivative is what we probably want to put in there. Of the what? So the instantaneous velocity is the derivative of the what function? Position, or original, but yeah, position for the context here. Okay, yeah, it's in the context, I'd say, but yeah, we want to be careful. Position for more specifics. Okay, if the acceleration of the particle is positive, then the blank is increasing. Velocity. If the acceleration of the particle is negative, then the blank is decreasing. Velocity again. Okay, in order for a particle to change direction, the blank must change signs. What function determines the direction your particle is moving? Velocity, right? If the velocity of the particle is positive, then the particle is moving to the right. If the velocity of the particle is negative, then the particle is moving to the left. So in order for a particle to change direction, the velocity must change signs from positive to negative or negative to positive, right? Speed is the blank of velocity. It's the absolute value. Okay, it's the absolute value of velocity, which is why if you go down if you drive forward in a car at 10 miles per hour, we say your speed is 10 miles per hour. And if you drive backwards in a car at 10 miles per hour, we say your speed is 10 miles per hour. But your velocities would be different signs. Okay? Your velocity, one way would be positive, one way would be negative. Okay? Because you're going different directions. But your speed we always refer to as being, absolute value of velocity. Okay? The amount of ground the particle covers is the position. Okay? And the change in the final position and the initial position is the net change. Okay, the net change there. Okay. And then let's see here. The particle speed is increasing when the signs of the velocity and acceleration are the same. Okay, so if you have positive velocity and a positive acceleration, your speed is increasing. Also, if you have a negative velocity and a negative acceleration, your speed will also increase. And we'll take a look at that here as we go on. The particle's speed is decreasing when the signs are opposite or different. Okay, they're counteracting each other. All right, so there's that. I think I want to keep going here. We're going to keep moving here. I want to try and get some of this done. I know we're really pushing to the bell here. I apologize, guys, but I do want to try and get some of these done here, okay? We won't get this whole one done. We'll just go for a few problems here. I promise I will stop and give you plenty of time to get, packed up if you need to and all that. But let's keep pushing along. All right, so example 9. The data in the table below gives selected values for the velocity in meters per minute, okay, so key units right there, right, of a particle moving along the x-axis. The velocity v is a differentiable function of time t. Okay? At t equals 0, is the particle moving to the left or to the right? What do we say here? To the left. Okay? Why to the left? What is negative? Velocity. Watch your pronouns in your explanation. If you say left because it's negative, you will not get full credit there. Because what's it? Right? Is it some scary clown? No, all right. It is the velocity in this case. So at time t equals 0, the particle is moving to the left because, and you can make it real easy and just say v of 0 equals -3. So the velocity is negative. Something like that. Just indicating that the negative velocity gives that away. Thank you. Okay. Is there a time during 0 less than or equal to t less than or equal to 12 minutes when the particle is at rest? Explain your answer. First of all, what does it mean for the particle to be at rest? Velocity is 0, right? Looking at this table of individual velocities, can we say that our velocity is going to be 0 at some point? How do you know between 0 and 2? The velocity changes from negative to positive. And because the velocity is a differentiable function, which means it's also continuous. What theorem allows us to say that it will cross through 0? Intermediate value theorem. Here's an application of it where we need to be able to use it appropriately. All right, I'm going to stop there because we're going to run out of time. All right. The homework is posted to Google Classroom, so please take care of that tonight. Okay. Any set requests for today before the bell rings and we're all rushing out of here? Anyone want to come in for set and get some help with anything? Emily, Ariana, and Cece. Okay. Okay. Anybody else for set? Chase. Other sets? All right, Cece. You got it. Morgan? Yep. Okay, anybody else for set? If you change your mind, let me know. Okay, if you change your mind, let me know.
I have a question about the... Some of them had, like translation marked off, but then others didn't.
Yes.
But like, and then the points
I
were
forgot to
taken off.
slash it. Oh, the points should not. I did not take a point off for those. Actually, I didn't count it against them. When I was,
Okay.
So yeah, should be okay. So thank you for noticing that, though, Cece.
I know you're a busy man,
I mean, it was sarcastic.
but
No, that's fine. I'll just.
I need a.
Letter of recommendation. Yes.
You see the email that I sent you?
Yes.
All right, cool. Yeah.
Yes.
I know.
ASAP.
Yeah, it is due tomorrow by 5 p.m.
Okay,
so just
I can.
anytime.
Because I feel like I've already written one
Yeah,
for you.
I think you did, but
So
it just like.
I gotta do it. Just use that.
All right, cool. Thanks.
Katie, what's up?
I was screwing around with my calculator trying to figure out derivative stuff on it.
Uh-oh.
And I noticed a function called convert to base.